Welcome back. Our next topic is complex matrices, and in particular Hermitian matrices. So I'm going to start with a very quick review of complex numbers. So we write a complex number as a plus ib, and the complex conjugate is a minus ib. Z times the complex conjugate z bar, which is a plus ib times a minus ib. If you work that out, you get this, and you get a squared, and then the middle two terms cancel, and I times minus I is plus 1, so you get a squared plus b squared, which notice is a non-negative real number. So we're going to write z with a bar or 2 bars for the absolute value, and that's going to be a squared plus b squared, the square root of a squared plus b squared. So we have this identity that zz bar is absolute value of z squared. Another fact, which is kind of handy, is if you multiply z times z bar over absolute z squared, you get zz bar over zz bar, which is 1. So that tells you how to compute the inverse of a complex number. You divide z by the real number, absolute value of z squared, z bar. So for example, 1 plus I inverse is 1 minus I over 2. And the final thing about basic complex numbers is the polar decomposition. You can write a complex number as r e to the I theta, where r is a non-negative real number and theta is between 0 and 2 pi. And I'll draw a picture to remind you how this goes. If you draw the complex numbers in the x plus iy plane, the point xy, or x plus iy, well, you compute r is the square root of x squared plus y squared, which is to say the absolute value of z, and the tangent of theta is y over x. So theta is tan inverse y over x, but make sure to make it between 0 and 2 pi. All right, so let's go on to discuss complex vector spaces. So Cn, of course, is just the n tuples of complex numbers. We've already used this a bit. And the important thing is what the notion of length of a complex vector is. So let's talk about that for a minute. What is the proper notion of length? Well, remember in Rn, the length of a vector, it's the square root of x1 squared up to xn squared. And notice that the thing on the inside is a non-negative real number, and so it has a unique positive or non-negative square root. If you do the sort of naive thing in Cn and define the length of a vector to be the square root of z1 squared plus zn squared, you immediately run into trouble, because this number z1 squared plus zn squared is complex. And there's no decent, unique way to take a square root of a complex number. That's one problem. Another big problem with this naive definition is the following. Notice that in Rn, a vector is 0 if and only if the length of a vector is 0 if and only if it's the 0 vector. But in C2, for example, you could take the vector 1i, and with this silly definition of length, the length of this vector is 1 squared plus I squared, which is 0. So you'd have a vector of 0 length, and that's definitely bad. So that's obviously not the right thing to do, but it's kind of clear what you should do. We need to somehow get a non-negative real number so we can take its square root. And the natural thing to do, well, let's see, in C1, what did we do? We plotted it like this, and we defined the absolute value of a complex number to be the square root of x squared plus y squared. Well, a vector is, if you take the length of a vector, it's a generalization of this. This is a 1 vector. So to generalize this to an n vector, it's clear what to do. If v is z1 through zn, then the length of v had better be the square root of the absolute value of z1 squared up to ... zn squared. Now that's a decent definition. The thing on the inside is a non-negative real number, and so it has a unique non-negative square root. Yeah. And to be explicit, this thing, it's x1 squared plus y1 squared plus dot 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 up to yn squared. And the square root of that whole thing if you write each zi as xi plus yi. Okay, now another thing to notice that in Vn, another way to write the length squared is v dot v, or we wrote that as the inner product of v and v. And so let's see how that carries over to Cn. You can't use the same formula because v dot v is z1 squared through zn squared, not absolute value of z1 squared, and so on. So we have to modify this. Okay, so how do we do that? We want to get absolute z1 squared through zn squared. Well, that's z1 bar z1 up to zn bar zn. And so you just write that as z1 bar up to zn bar dot with z1 through zn. So it's just like what we had before, except you have to put the bars on one of the terms. And I'm going to emphasize column matrices here. And so if you use column matrices, we write this as this vertical vector here is v, and then this vector here is transpose bar. So the formula for the length squared is v transpose bar times v.